All right, guys, so let's get into our next type of function here, which is it's going to be polynomials. So far, in algebra, we've probably studied linear functions, y equals mx plus b, and then go on to quadratic functions that have the x squared term in there. And those are all polynomials, but what polynomials allow you to do is just get higher powers, basically. We're going to talk about their end behavior, meaning what happens on the end of these graphs. Are the ends like you think about a quadratic? On the ends, the end may be going all the way up and up and up on both ends. You may have a graph that goes down on both ends. On linear functions, for example, you may have one end going up while the other end is going down. That would be just something with a positive slope. Okay, we'll talk about like how do we determine what the end behavior is. Like if you didn't even have a graph, there's a way to look at the equation and just kind of decide some of that stuff, and that's important. It's actually a big idea in calculus even. It's called the limit of a function. So as the x values get bigger and bigger, if you think about a graph here. So as the x values go 1, 2, 3, 4, 5, as x just continues to grow, what are the y values doing? In this case, they're going to continue to grow and grow and grow and so on. Then we'll also talk about intercepts. We've talked about x-intercept, y-intercept, same kind of thing. We'll be able to find some of them algebraically, solving equations and doing some work. But for the most part with polynomials, since they are a little more complicated equations, we're going to rely a little more on technology. So we're going to use Desmos to do that. But like for linear equations, it's pretty easy. If it's in y equals mx plus b form, we know the y-intercept is just that b value there, and we can find an x-intercept by plugging in 0 for y. Okay, and then with quadratics, we talked a little bit too how that c value is going to be the y-intercept, and then x-intercepts can be found by factoring or quadratic formula. And then the other important thing with these polynomial functions is extrema. Just a fancy word, like extreme is like the highest or lowest, or like a max or min. And we did this with quadratics, right? Wherever that vertex was at, that would be a minimum or a maximum, depending on the way that the function, the way the graph opens. And with linear functions, they don't necessarily have one, right? Because they're going to be increasing to infinity and decreasing, so it doesn't ever really have a minimum or maximum. So let's take a look at a couple examples and see what we can do. And again, we'll be using Desmos to help us out with the graphs, but we just need to know how to analyze them and answer some properties about them. All right, so here's an example of a polynomial. Okay, you see the equation over here on the left, y equals 3x to the fifth minus 2x minus 2. So it gives you an idea of what a polynomial function looks like. It's basically, it's like a linear function or a quadratic function, but it can have higher powers on the x, as long as the power is a whole number and you don't have any variables in the denominator. It's basically going to be a polynomial function. This one happens to be of degree 5. That's what the biggest exponent is, a fancy word. It's the degree. Okay, so linear functions are basically just first degree polynomials because they're y equals mx plus b, right? It's just x to the first power. And then quadratics are second degree because they have x to the second power as the highest exponent. So some things to notice when you type this into Desmos, when you graph this. If you go over and click on the graph, it'll give you those special points you see. You don't even really have to do any work. Like it's a lot more work on the graphing calculator to get those coordinates. But on Desmos, you can just mouse click right on there, just tap it, and it's going to give you, like I said, all the important features. So it's giving us a few things. So we have the intercepts. Okay, we see right here. This is going to be our x-intercept right here. And just be careful, it looks like, if you just glance at it, it looks like it would be x equals 1. But when you actually click the point, you see it's actually slightly bigger than 1. So don't just assume it's always going to be a nice whole number. And then down here at 0, -2, that is going to be the coordinates of the y-intercept. Okay, and that one's just going to be the constant term here. Constant meaning it doesn't have a variable attached to it. It's just like a number. Okay, so those are your intercepts. The other 2 points that it gives us are the extreme values, the mins and maxes. So this point right here, okay, coordinates as you see, this is a maximum, okay, because it is the highest point. It's kind of like the vertex, right, of a little quadratic. It's the highest point for a region of the graph. Like if you look at the graph here, that would be like the vertex of it. Now here's the thing though, it's not the highest y value this graph ever gets, right? This graph over here, if you can see, keeps going up and up and up. So what we do, we don't say that as an absolute maximum. Okay, there's a special word, there's two options. We either call it a local maximum, okay, or a relative maximum. Okay, so it's like the maximum of points near it. Okay, so that's why it's like local, like of the nearby points, that's the highest. And the actual max would be the y value. Okay, the x value is just where that y value occurs at. Down here, on the other hand, this is, if we take a look at the graph, as it's coming down and then comes back up, that's kind of like the vertex again of a parabola opening upwards. So that one is going to be, again, it's not the lowest y value ever, right? There's lower y values down here, but this y value right here is, again, a local or relative minimum, okay? The x value is just where it happens to occur at, but the actual minimum, the relative minimum, is the y value. Okay, so one thing I want to point out though on this function now, this new thing, this idea of end behavior. Okay, this is something that's, again, I was talking about, it's going to be a little bit important in calculus when you talk about what is the graph approaching in the long run. So meaning, if the x values just continue to get bigger and bigger and bigger, what are the y values approaching? So what I want to take a look at is on the ends of the graph. Let me see if I can use like yellow here. Okay, on this end of the graph, you see that graph's just going up and up and up, and on this end of the graph, the left end of the graph, is just going down and down and down. Okay, now what ends up happening is whenever you have a function that has a odd degree, okay, this one degree was 5, right? That's an odd number. Okay, whenever the degree is odd, the function's ends will always go opposite directions. Okay, one end's going up, one end's going down. Right? Think of like a linear function. Right? On a line, one end goes up, one end goes down. Okay, when the degree is even, okay, like a parabola, like x squared, right? 2 is an even number. Both ends go up, okay, or both ends go down, but they go the same way. Okay, so odd degree means the ends are opposite. You can remember that O opposite, O odd. Okay, and what we can do, or the way we want to write that, is kind of a fancy way. We're going to say as x goes to infinity, and we're going to use this arrow for like approaches. As x approaches infinity, okay, that means, think about as x gets bigger, the x-axis gets bigger to the right. So as x goes to infinity is just a fancy way of saying to the right. We're going to state what are the y values doing. Okay, on this graph, we can see right here, the y values are going up and up and up, so they are also going to infinity. Okay, that's the right end behavior. There's always two statements though, because there's always something going on the left end as well. Okay, so on the left end of the graph, over here, as x goes to negative infinity, right? That's what happens on the left side of a graph. On the left side, think about the x values just going to negative infinity. That just means left. In this example, the y values are going to negative infinity as well. Okay, so that's how end behavior works. You're always going to have these two statements. There's going to be, these are like be locked in. You're going to decide, you're going to write what are the y values doing. Okay, there's always one statement as x goes to infinity and a separate statement as x goes to negative infinity. You determine what the y's are doing. Okay, so let's look at one more example. Here's another example. This one, y equals negative 5x squared plus 2x plus 6. This one's just a straight quadratic like we did some earlier in the year. Okay, so you can see it's a parabola. You can see both ends are going down. So if we just wanted to kind of highlight that, on the left end here, graph's going down. On the right end here, graph's going down. Okay, and that happens because it's an even degree function. Okay, it's an even degree function, so both ends are going to go the same way. Okay, if it was 4th degree, both ends would go the same way. If it was 6th degree, both ends would go the same way. Okay, they might both go up, they might both go down. The way to determine that, if you wanted to tell without even graphing it, what we look at is this leading coefficient, the negative 5x squared term. The negative 5 is the leading coefficient. Since it's negative, that's going to tell you what's happening on the right side of the graph. Okay, negative leading coefficient means that on the right side, the y values are going to be going down. Okay, negative coefficient means the right side goes down. So we write that as x goes to infinity. Remember, that's just a fancy way of saying right. Oops. There's my pen. There we go. We know the y values are going down. Okay, so that's what we do first. We look at that leading coefficient. Since it's negative, right side goes down. Then what I look at is, since the degree is even, right, it was a 2nd degree function, that tells me that the left side, okay, which is as x goes to negative infinity, since the degree is even, I know the left side has to do the same thing. So the y values are going to go down as well to negative infinity. Okay, so you can kind of determine some of this stuff even if I didn't have the graph. Okay, now of course you can always get the graph too, but even if you didn't have the graph, you could go through that process where you look at the leading coefficient and then you look at the degree, and it will tell you the end behavior. Okay, let's make up one last one. Let's do one without even having a graph. Let's say it is, for example, y equals negative 2x to the 3rd plus 6x squared minus 14. Okay, for the end behavior, which is kind of the new concept, okay, you can always graph it and just piece it together like we did before, but really you don't have to. Okay, all we're looking at for end behavior is this first term, the one that has the biggest exponent. So if it's not in the right order, you know, always get the term with the biggest exponent. Okay, standard form would have that term written first, but it's not always the case. So what I'm going to do first is I'm going to think about, since the coefficient is negative, that tells me the right side of this graph is going down. Okay, and we write that in the fancy notation as x goes to infinity. That means x getting bigger to the right. We know the y values are going negative. Okay, so we look at that first. Then what I'm looking at to figure out the left side of the graph, I'm looking at the degree. Okay, the degree is an odd number. Odd degree means the left side needs to do the opposite direction, so it needs to go up. So on the left side, as x goes to negative infinity, in this example, the y values are going to positive infinity. Okay, now I don't know about the x-intercepts and the max and mins and all that stuff. I don't know, in other words, we don't know what's going on in the middle of this graph unless we did some more research or graphed it. But as far as end behavior, we can determine that stuff just by looking at this leading coefficient and the degree. Okay, I would encourage you guys to just throw it in Desmos just to be sure. Again, it should kind of be able to be done, at least the end behavior portion, without graphing it. Okay, and one thing I'm noticing, just to kind of be picky while I'm thinking about it, the y-intercept would be negative 14, so it would be crossing down through here. So my little sketch in the middle there is obviously not accurate, but you know, we did know a little more information on it. All right, so that's end behavior. Again, you just look at that leading coefficient. Okay, first step, is it positive or negative? That'll tell you what's going on the right end of the graph. And then the degree being even or odd will tell you what's happening on the left end. All right.